Assalamualaikum, selamat sejahtera to all students. So in this video, I will continue chapter 3, liquidity extraction. So I will continue on the single stage of LLE. Okay, so liquidity extraction, we have two types of stage. We have a single stage and also we have multi-stage. Okay, usually in single stage, we want to know the composition of the extract and raffinate. Okay. However, in multi-stage, usually we want to know how many stages involved in multi-stage LLE. Okay. So in the single stage of LLE, okay. So you can read the explanation. Okay. I will make it short. Okay. So single stage is solvent and feed stream are contact in each other. Is of course as I mentioned in the previous video. Okay. LLE is the is a process where the solvent here and the feed will contact with each other. Okay, feed containing component A and B, while the solvent, it can be pure or it can have a low concentration of solute A. Okay, so feed usually will contain a solute A and B. Okay, so A is dissolved in B as a carrier or as a diluent. Okay, and solvent we put as component C. Okay, if the solvent is a pure solvent, means it only has a component C. Okay, or if the solvent is not pure, it may contain a low concentration of solute A. Ada sedikit, there's a little amount of solute A in the solvent. Maybe this is a recycled solvent. Okay, so usually we use pure solvent as to extract the desired component A. Okay, so when the feed and the solvent mix, it will form an intermediate phase. As I mentioned in the previous video, we call it as M. Okay, so from what happened during this phase is actually the light liquid move through the heavy liquid in the form of bubble. So the bubble provide a large surface area for contact between the feed and the solvent that speed up the mass transfer process. So this is the detail behind the process of LLE. Okay, when the feed and the solvent has mixed together, so A will soluble. It will soluble into solvent C. Okay, so this is the detailed process. Okay, in most single LLE, okay, we are interested to know the equilibrium composition and the mass flow rate of the extract and raffinate. Okay, so in single stage LLE, usually the calculation, we want to calculate the composition, the mass flow rate of extract and raffinate by using diagram. We call it as ternary phase diagram. Okay, and also we will use the mass balance principle. Okay, so the phase diagram, we have a right triangular and we have equilateral. Okay, I will show both of them during the calculation. Okay, so this is the flow diagram for the single stage. Okay, if you can see here, if in this diagram, okay, so let's say this is because of we have a single stage LLE, so there is only one stage here, LLE 1. Okay, so I will put 1. So L node is actually the feed, so feed is being denoted by L node. Okay, because it comes from the tray 0. So the raffinate here is really known as L1 because it exits from the tray 1, so we put L1. And the solvent here, we put as V2 because it comes from the tray. Even though there is no tray 2, but we know that it's actually from stage outside from stage 1. Okay, so we put V2. and the extract we put as V1 because of it comes from stage 1. Okay, so we put V1. Okay, so in terms of the mass balance, if I can draw for you, okay, so this is feed L node, this is raffinate L1, this is solvent V2, so this is extract V1. Okay, if I want to construct the mass balance, okay, mass balance. Okay, and another thing that you should know that, okay, when we mix L node, which is the feed, with the solvent, which is V2, it will form a M. Okay, so the M eventually it will form V1 and L1. Okay, so M is the intermediate, okay, the intermediate mixture that I just mentioned, that I mentioned just now. Okay, so in terms of the mass balance, let's construct the overall mass balance first. Okay, in is equal to out. Okay, you will notice in is actually L node plus with V2. Okay, so it will become M, and M also is equal to V1, which is out, plus L1, yes, okay, L1. So this is overall mass balance. Okay, you will notice there is an M, okay, because of it forms an intermediate mixture here before it forms two types of product, extract and raffinate. So we put M as a part of the mass balance. Okay, now we will do the mass balance on component A. Okay, so in terms of the mass fraction, we will put X A node, X B node, X C node. So here is X A1, X A2, X B2, X C2. 1. Okay. This one is YA2, YB2, YC2, and this one is YA1, YB1, and Y1. Okay, if I want to do the mass balance on component A, so it will become L node times with XA node plus with V2 YA2 YA2, okay, equal to M, we will multiply with X AM, okay, equal to V1 YA1, okay, on component A, plus with L1 XA1. Okay, so this is on the component A. Okay, on component C, because of we don't know about B, because of we know that if we can find the value of A and C directly, we can know the value of B. Okay, as I mentioned during the class. Okay, so for component C, it will become L node XC node plus V2 YC2 is equal to M, XCM equal to V1 YC1 plus L1 XC1. Okay, so we have three types of mass balance: the overall mass balance, the mass balance on component A, and mass balance on component C. So we will use this mass balance to solve, okay, to solve for either the equilibrium composition or the mass flow rate. Okay, we can use the mass balance. Okay. Okay, what else? Okay, in single stage, okay, we want to know, we can find two types of information. Okay, we can find the raffinate R and extract composition, and we can find the mass flow rate of our raffinate and extract. Okay, both information, the composition and the mass flow rate, we can find in a single stage. Okay, the composition of raffinate and extract, we can use graphical. Okay, we can use graphical. I will show you later. Okay, in terms of the mass flow rate, we can use the mass balance that we just construct just now. Okay, we will use mass balance. Okay, let's see the example 1. Okay, let's continue on example 1. So let's read the question. So example 1 is 100 kg of solution containing 0.4 mass fraction of Eg, ethylene glycol, in water. So Eg is component A and water is component B. So as a B, component B is as a carrier or diluent for the ethylene glycol. Okay, so it's to be extract with equal mass on fulfuril. So fulfuril is the solvent. Okay, we put as component C. Okay, so the mass for component C is equal, which is also 100 kg, same like the feed. Okay, so extract at 25 degrees C and 101 kilopascal. Okay, using the ternary phase equilibrium diagram, so determine the composition of the raffinate and extract composition, and determine the mass of raffinate and extract. Okay, and the percent of component A being extracted. Okay, as I mentioned before, so in order to know the composition of raffinate and extract, we will use the phase diagram. Okay, the phase diagram. Either we have a right triangular and the equilateral. Okay, and the mass of extract, we will use mass balance. Okay, let's see how is the solution. Okay, this is the equilibrium data. So when you are given equilibrium data as like this, you can plot the equilibrium curve and the timeline. Okay, so let's see, let's do the solution. Okay, so first, when you get the question, so you put first you construct the process flow diagram. Okay, so I will put here is L0 as a feed. So this is L1, so this is V2, so this is V1. Okay, so L0 is the feed. So L0 contain 100 kg, okay, mass, and 0.4 is a component A, which is ethylene glycol, and the water contain 0.6. I put as component B. Okay, so next, it use fulfuril as a solvent, so it is component C, so it has 100 kg also, and I will put C is 0. Okay, so A, B, C, 0, 0 and 1, because it is pure solvent. Fulfuril means C is equal to 1. Okay, so this one I don't know the composition of A, B, C and the composition of A, B, C. Okay, I cannot, we haven't identified yet. Okay, the first question is to find the composition of extract and Refinite means V1 and L1. So this is extract, this is refinate. Okay, composition means is the fraction of A, B and C. Okay, so this is the composition. When you put the answer, you should put what is composition of A, B and C in extract and A, B and C in refinate. Okay, we will use the graphical method. Okay, so first, before we go to the graphical method, we should find M. Okay, first you construct a mass balance. Okay, I will put overall mass balance. Okay, L naught plus V2 is equal to M. Okay, M is equal to V1 plus L1. Okay, so but I don't have this, I will only use this as the overall mass balance. Okay, next L naught, I will do a mass balance on component A. L naught X A naught plus V2 Y A2 is equal to M X A M. Okay, let's solve this first. Okay, L naught is 100 kg plus V2 is 100 kg is equal to M, means M is 200 kg. Okay, so L naught is, we solve this. Okay, next we will solve this. Okay, L naught is 100, XA naught is 0.4 plus V2 is 100 and YA2 is 0, M is 200 and XAM is the one that we want to find. Okay, so from here this is 0. Okay, so this is 40 is equal to 200 XAM. So XAM is equal to 40 divided by 200, which is 0.2. Okay. Okay. Now let's do a mass balance on component C. Okay. Component C. On component C, L naught X C naught plus V2. Okay, V2 Y C naught is equal to M X C M. Okay, so the overall balance is M is 200. Okay, so now L naught is 100. We times with C. L at N, L fit at fit is 0, so we put C is 0 plus V2 is 100. YC naught is, here is 1. Okay, so we put 1. M is 200 and XCM. Okay, so this is 0, so this is 100 is equal to 200 XCM. So XCM is equal to 100 divided by 200 is 0.5. Okay, now the mixture, you have the composition of component A, which is 0.2. Component B you don't know, and you have a component C which is 0.5. So from here is actually you can find the component B by subtracting 1 with 0.2 and 0.5, and you will get here is 0.3. So this is component A, this is component B, and this is component C. Okay, so before we proceed to the graphical method, you must find the M first, the composition of M first. Okay, you will know later what is the function of M. Okay, after you get the M coordinate, next you proceed to the graphical method. Okay, so this is the graphical method. This is right angle method. Okay, so right angle method, as you can see here, the equilibrium curve has been constructed. Okay, so it also has a tie line here. Okay, so here I think there is a mistake here. Usually this will be on component C. This is component A, but here it becomes vice versa. Okay, so this is component A, this is component C. It's okay, we just follow. Okay, let's see on how to construct the how to use the graphical method. Okay, first, of course, you should have the equilibrium curve. Okay, you should have the equilibrium curve and the tie line lah. Okay, so this is the basic. Okay, before you should proceed with the graphical. Okay, next, okay, you locate first. You locate the point feed, which is L node, and the solvent, which is V2. Okay, so here it denote as F, which is the feed, and V2 is the solvent. Okay, feed and solvent. Okay, so you go back to your diagram. So your feed, okay, so in right angle method, we only considering component A and C, so we don't bother about B. So the coordinate for feed is 0.4 for A, C is 0. Okay, so feed 0.4, so 0.40 is here. Okay, and for solvent, it actually A and B is 0, so C is equal to what? So C for solvent, the coordinate is here. So you join these two line. Okay, these two dot you join by a straight line. Okay, so next you locate the point M. Okay, point M, you already find the coordinate here, 0.2 and 0.5. Okay, so you find 0.2 and 0.5 here. Okay, so if you don't have the full coordinate, it's okay. Actually, point M will lies on the FS line. Okay, it will lies on the FS line. Okay, you can see you join F and S, the feed and solvent line, you draw, and M will lies on this line. Okay, so if you don't have the coordinate, it's okay, you can put the M on this line. Okay, if you, let's say M, you only have the composition of A. Let's say you only have 0.2. Okay, you have 0.2, but you cannot calculate B and C. It's okay, so you put 0.2. Okay, so when 0.2, M should be here because of it will lies on the line. Okay, anywhere on the FS line. Okay, so in this case, I will calculate M. So I already have the M coordinate. Okay, so 0.5 and 2 here. Okay, next is you draw another line. Okay, so you draw another line that cross the M. Okay, you draw another line, the green line across the M. Okay, this another thing that you should aware is the green line should lies in between the tie line. If you can see, here is a tie line, so here is the tie line. So how you should draw the green line is you take the intermediate between this point to this point here, and here this point to this point, you take middle point, and you join the green line, but it must cross the M. Okay, so you should put your ruler on M. Okay, and you should adjust the ruler so that the point here and point here should lies in between this point and this point, this point and this point. Okay, so the green line should lie in between, in the middle of the two tie line, but it must cross M. Okay, that is the condition. So the point here is your extract composition, and the point here is your raffinate composition. Okay, so you can read this point. Okay, so this point you can read the coordinate, so you will get 0.26 and C is 0.68. Okay, something like that. Okay, so raffinate, maybe I cannot see clearly the point. Maybe 0.098. Okay, here sorry, this is for component C. Component A, something similar, 0.098. Okay, 97 or 98. Sorry, 0.0 now here. Okay, so you can answer the first question. So the composition of the raffinate and extract. So this is the composition. Okay, here and here means this is A, this is C, this is A, this is C. Okay. Okay, next we will look into equilateral triangle. Okay, the same thing, the same step you will apply. Okay, first you should have the equilibrium line and the tie line. Okay, next you should locate the feed and also the solvent point. Okay, so the feed is here. Feed, if you can remember, feed is 0.4 component A, 0.6 component B, C is 0. Okay, so for solvent it's 0, 0, 1. Okay, so let's see. Water is 0. A is 0.4, and water 0.6, and the C is 0, means the F is here. Okay, so F is here, and the coordinate for S is 0, 0, 0, 1. So the coordinate is here. So you join them, S and F. Okay, and you put, you know that M is 0.2, 0.3, 0.5. So the coordinate of M here is A is 0.2, sorry, 0.2. Fulfuror is 0.5. This is 0.3. So the coordinate of M is here. Okay, is here. So it lies on the FS line. Okay. Okay, next. Okay, we already locate M. Next, we make a straight line. Okay, raffinate and extract, the same thing. So you put, you make the green line that cross M. On the same time, it lies in between of these two tie line. Okay, this tie line and this tie line. So this is extract coordinate and this is raffinate coordinate. Okay, so you will get these two composition, extract and raffinate. Okay, and number 5, you find E and F coordinate. Okay, we will basically we have the same coordinate as the right triangular method. Okay, so next you already find composition of E and F, okay, by using this method. And when you read the coordinate for both graph, you will get this coordinate. Okay, so E abstract is 0.26, 0.68, okay, 0.06. This is A, C, and you can find B. Okay, so for definite is 0.075, 0.075, and B is 0.85. Okay, so this is the composition. Okay, next we will do a mass balance to find the value of the mass flow rate for extract and raffinate. Okay, we will do a mass balance. Okay, so let's start with L naught. Okay, so L naught X A naught plus V2 Y2 M L1 XA1 plus V1 YA1. Okay, so this is the mass balance. Now we want to know the L1 and V1 value. Okay, so you know M is 200, so you can use this. We can use this equation. So this is on component A, So on component B, it will become L naught component C, XC naught plus V2 Y C2 is equal to M. Then XAM, XCM equal to L1 XC1 plus V1 Y C1. Okay, so this is on component C. So okay, I will take this equation. So M is 200, XAM is we already find XAM is 0.2, okay, is equal to L1, we don't know. XA1 is XA1 is extract, so 0.26. We put 0.26 here. Last V1 we don't know, and L1 is raffinate. This is raffinate. This is extract. Okay, I think I put the wrong value. So this is L1 is 0.075, 0.26. So this equation 1. So 200 on component C, 0.5 is equal to L1 component C, 0.68. Sorry, 0.75, 0.075 plus V1 0.68. This is component C. You take this one and this one, this one and this one. Okay. So this is equation 2. So you can solve this equation. You can find L1 and V1. So you will get L1 is equal to L1 means the raffinate. So 64.86. Okay, 64.86 kg, and V1, which is the extract, is 135.14. Okay, 135.14 kg. Okay, so you can solve by yourself. Okay, you can solve these two equations and you will find the value of the unknown. Okay, so for the percent of ethylene glycol extracted, so you can use the formula if you want to know how many ethylene glycol has been extracted, so you can times, okay, here this is L naught, okay, so X A naught, X A naught, this is B1, okay, this is L1, this is B2, this is B1. Okay, so if you want to know how many ethylene glycol has been extracted, you multiply V1 with Y, the composition of A here, YA1, okay, you multiply, you divide by here L naught, XA naught, you times with 100, okay. So V1 is you find here 135.14, you times with YA1 is actually 0.26, you divide by 100, L naught, XA naught is 0.4, okay. So you will get the value here, so 87.8. Okay, so the percent of ethylene glycol that has been extracted by perforant. Okay, that's all. Thank you.